Hello everyone, welcome back to a new tutorial here in Max. Today I would like to talk about delays. Now, delays are a very cool way of processing audio, and you can experiment a lot with them and do lots of weird and crazy stuff. And today I just kind of want to give you the basics of how delays work in Max and some ideas how you might creatively use delays in Max. So for starters, I have set up this little Max patch here. So basically here at the top, we have an audio file, which I played in just a few minutes ago. It's a little road sample. It's nothing special, so we can listen to this real quick. Yeah, nothing special. And so this is kind of being output as a raw unedited mono file. We're just putting out the left channel. And on the right hand side here, we have a delayed signal. So I'm utilizing here the delay object, and the incoming signal will then be delayed by this object and output. And this sounds like this. Still nothing very special, but it's the most basic kind of way on using delays in Max. So in this case here, as you can see, I'm using this delay object, and it basically takes any kind of incoming signal on the left inlet, and it will delay that signal by a certain amount of time given in samples. That's very important. So we specify the delay time in samples and not in milliseconds. So if I create this object again, you can see that the first argument that it wants is going to be the maximum delay memory. So basically what happens if we feed a signal in here, it's kind of writing this in real time into a buffer, which we have to specify its length. So in this case, let's say, for example, 48,000 samples, which is corresponding to 1 second because my project is set up at 48 kilohertz as a sample rate. So this will be 1 second of audio. And now the second argument is going to be the initial delay time. So this will specify the delay time. And in this case, for example, we could say I want a second of a delay, and that would be again 48,000 hertz. So this is exactly what happened here in the example I just played you. It just delayed the signal here by 1 second. So this is already really cool, and you can already do a lot of things with this. For example, the most simple kind of additional thing we could do is we could create a stereo delay. So for example, we would duplicate this delay object and just input the second object into the right channel, and then we could, for example, adjust this delay time to maybe, let's say, half a second, so 24,000 samples, and that will create now two delays. On the left hand side, we would receive a delay of 1 second, and then the right hand side, right channel, a delay of half a second. So really cool already what's happening here, right? It's very, very simple, but it's already a stereo delay. And of course, what we could do is we could even further expand this and say, let's make a multitap delay out of this, create 3 more delays with different kind of delay times, and this once again will create interesting sounds, and we can arrange this again randomly onto the left or right channel. So let me do this real quick. So I utilized 3 new delay times. One's a quarter of a second, and the other ones are just kind of a little bit of a spicy random kind of time. So this will sound like this. So really cool. This is already a multi-tap delay of sorts. And now you can really push this to its limits and try all kinds of different things. And I think that's already really cool. Now let me delete this all and showcase you a additional feature that we can use with this object, and that is its right inlet here. This right inlet allows us to externally kind of adjust the delay time in samples, of course, again. So for example, for now we would maybe want to adjust the delay time manually more easily, and also adjust it in milliseconds, because I mean, I don't think any of you guys is actually thinking in terms of samples, and I think we're all thinking in terms of milliseconds or seconds. So let's utilize an object called ms2samps. This allows us to translate any given value in terms of milliseconds and translate it into samples. So in this case, for example, if I think of 1000 milliseconds, which is corresponding to 1 second, that would give us 48,000 samples, and that's exactly what this object does right here, right? So we could just take this and put this inside this inlet, and now we could just adjust the delay time a bit more easily like this. So let me do this, because as you will hear, there is an issue if I adjust the delay time while it's playing. So the first thing that you're probably realizing is once I go beyond 1000 milliseconds, so 1 second, we hear kind of like this metallic artifact kind of sound. And that is because we're going beyond our delay, maximum delay memory, right? So it is specified here as 1 second, 48,000 samples, and that is corresponding here, not corresponding here with our value that we put in here. So it's above and beyond the maximum, and that is what creates these kind of weird noises. And the other thing that you've realized is that once we move this up and down, there are clicks introduced, and these clicks, they're here because we're essentially jumping in sample steps that are quite big, right? So in order to make this clickless, we want to introduce a line object to smoothen everything out. So essentially what we're going to do is we're going to have the line object, and with a message object we can say the incoming value that we're taking will be smoothened out by a ramp of 20 milliseconds. And in order to have a number here, we will have to translate this signal to number, and we can use the snapshot object here, which translates signal values to number values. And we have to specify a reporting interval, in this case 20 milliseconds, for example. So every 20 milliseconds, the signal value will be put out as a number value. And then we can put this back in here, and now we have a smoothened transitioning of samples, kind of. That is not insanely jumping anymore, and you will hear this as well. Now, there are no more clicks. And as you can see, very interesting sounds are being created here. So this is very cool, and we can, of course, work with this. So, for example, this opens up a lot of new possibilities. We could say, why don't we use a sine wave to modulate our delay time? So the sine wave here, for example, we have a rate, a frequency that is very low, so a very slow oscillation. So sine wave signals, they essentially put out values between -1 and 1. So right here, the middle is 0, so it goes all the way down to -1 and up to 1. And in this case, we could scale these values with the scale object. So scale -1 to 1 between, now in milliseconds then, 0 to 20 milliseconds. So now the values are being scaled to these two numbers. Now let's input this here into ms2samps, and as you can see now, the delay time is being modulated by this cycle object here. Let's hear how this sounds like. Let's introduce our previous original audio here as well. Interesting. this sounds like a phaser or kind of like a flanger or something. So delay doesn't automatically mean or kind of represent the idea of what we think a delay might be, because, well, this graph kind of represents this very nicely. At lower delay times, you can see here on the x-axis, you will see delay time, and around it, there are different kind of audio effects that are correspondingly being created by these delay times. So you can see between 1 and around 30 milliseconds, we don't actually hear any delay as we know it, or like an echo effect, and rather we are creating phasers, flanger, and chorus effects. So they are built upon the idea of a delay, but they're not actually what we might consider the classic kind of delay. So that's very cool, because what we essentially created here is a flanger, and of course these three effects are a bit more complex than just, you know, adjusting the delay time. This, what we did here, is comes close, very, very close to basically a flanger. And of course we can you know, like experiment with this and adjust, for example, adjust the sine wave here, the rate at which it's going, and well, now it's actually very interesting. We can also adjust here the scaled values. Maybe increase them to maybe, I don't know, 100 milliseconds. And then we can increase this number here. Okay, now this is too fast. Very interesting, I would say. Maybe not, no, sorry, let's say 50. Maybe we can also increase this to 1,000. So very cool effects that we can create just by simply modulating the delay time. And now experiment with this, really, like adjust this to be, you know, not a sine wave, but maybe a triangle wave, or a phaser, or a square wave, whatever it is, really. And of course, also maybe you could utilize something like noise to use random values, right? Jumping between them and like morphing between them and whatever. So this is really like just opening up so many possibilities already by utilizing this right hand inlet here. And of course you can expand this again to be a stereo delay, and so on and so forth. Now, one thing we haven't talked about yet, which is a kind of very much a classic when we're talking about delays, is feedback. So feedback essentially is when we take a delayed signal, so that would be here the outlet of the delay object, and we feed that back into its inlet. So we delay that signal again, and then we automatically delay it again and again and again, over and over and over. Now in Max, we can do this very simply. Unfortunately, the delay object doesn't work for that, so we cannot use this for feedback. We would have to use the delay object inside of Gen, but this might be something for another lesson. So for now, I'm just going to kind of delete the delay object and utilize and showcase you the second way to create delays in Max, and it, in my opinion, also the more versatile and kind of also the more, I think, common way of creating delays. And that would be with the tap in and tap out object. So these work incredibly close to, or very similar to, the delay object. In this case, it's not just one object, but two, and they have a couple more features. And so the first object here, the tap in, it sort of works like the first value that we had to give the delay object. So this is kind of the buffer. So any given signal that comes into tap in is in real time being put into a buffer, and we have to specify the length of that buffer. And now we're not considering the values in samples anymore, but in milliseconds. So for example, I would want a 1 second buffer or memory, kind of maximum memory. So that's basically here the tap in, what it does. And the tap out object then feeds or kind of references and takes the audio from that buffer and works with it to create delays. And so for example, we could do the same thing as previously with the first example, just create a 1 second delay. So let's connect this here to the outlet, and now if I start playing this, you will see that it's just a 1 second delay. So just like our previous first example with the delay object. Now, already there are a couple things that these two objects are doing a lot better than the delay. So for example, if we were to increase the delay time beyond our max memory, so in this case now the delay we would want is 2 seconds, but our max delay is only 1 second. So the tap out object in this case then, it doesn't affect the audio in any way. It will just stay 1 second, and it's not going to introduce any artifacts or clicks or anything. It's just going to kind of cap at 1 second, and it's not going to change anything, as you see. So that's already really cool. And also, the even cooler thing you can do with the tap out object is you can use multiple delay times in one object. So we could, for example, say I want a delay of 1 second, half a second, quarter of a second, and then some spicy values. So now, as you can see, 4 new outlets and inlets have been created, and that essentially these correspond to the delays that we just wrote. So we can then put them at random here again into our outlet, and now we have created a multitap delay with just one object. That's pretty cool. So let's see. Very cool. And of course, just like with the delay object, we can also adjust its delay time with these inlets here. So we can do this once again with a number box. So for example, let's actually remove these again, or we could just delete them like this real quick. So now we have just our first 1 second delay. Now, once again, we can adjust this here, and you see there are clicks again, just like previously. So what we would need to do is once again use the line object. There we go. So once again, the value that we want replaces here the $1 sign and it applies a 20 millisecond ramp. So as you can see, now the clicks are gone once again. So that is really cool. So once again, you could maybe, for example, use some kind of modulator to modulate the time. So for example, we could use this here again, but of course take out the MS2 SAMPS with snapshot, and or excuse me, only the MS2 SAMPS, because we don't think in samples anymore. And then we have milliseconds right here, so we can use this again to create the same kind of effects right here. And then of course we could do this with the other effects, the other delays as well, and have those for example be modulated in different ways, right? Like instead of this, we input maybe 200 milliseconds or something, between 10, like experiment with these things, and then we have like interesting weird stuff happening, and you can really experiment with this and kind of figure out what values work, what doesn't work, and so on and so forth. So that is really, really cool. And now let's talk about how feedback works. So as we previously mentioned, what it means is that we just feed any kind of delayed signal back into the delay. So we just take the outlet of tap out and put it back into the tap in. So what happens now is the delayed signal goes back into here, is being delayed again, and then it's being delayed again, and again. And what this will create in this case here is just kind of this ever evolving and clustering kind of sound of our Rhodes audio file. So what it sounds like is, this is the original again, and this is now the fed back. Very cool already. Now, the issue, of course, here is that the sound, the delayed sound, is just persistently staying here, right? And we might want to let it die out over time. And we do this by adding a multiplication tilde object by any kind of amount between 0 and 1. So in this case, we will connect it up to the output of the delay, and the feedback signal will be connected to here. So what's happening is, for example, the signal comes in here at an amplitude of 1. Let's just simply say it's 1. Now, it goes through this delay processing, it's being delayed, and when it comes out here, it will be multiplied by 0.5 or divided by 2, sort of. So the amplitude of 1 is then going to be 0.5, and then it's going to be a little bit like half the loudness, so to speak. It's going to be fed back into the delay, now at the amplitude of 0.5, and then it's delayed again and halved again. That means now it's going to be at an amplitude of 0.25, and so on and so forth, until it's basically just 0 and it died away. So this will sound like this now. So we still have the feedback, but it's not this cluster of sound anymore. And once I stop it, you will see that the sound has now faded out. So that's basically how this works. And of course, we can adjust this manually, this feedback amount, by inputting a value between 0 and 1. And 1 meaning it will evolve forever. So let's see. At 0, we will hear 0, nothing, because the amplitude is just, or like the audio signal is multiplied by 0. At 1, it will do the same thing as we heard without this multiplication. And be careful, if you go beyond 1, you basically increase the amplitude over and over and over and over again. Maybe I can... yeah, this was as terrible as I expected it to be. Just be careful to not go beyond 1. So in order to create, for example, a ping-pong delay, which is a very common use of delays, we would have to first create a stereo delay. We do this by just copy-pasting the objects here. So now we have one for the left and one for the right. And then, of course, we can experiment, for example, with different delay times again to just simply create and also with different feedback times, amounts. And now we have a stereo delay with feedback. And if we want a ping pong effect, we will just feed the output of the delay here, the feedback output, so to speak, then into the right feedback here, and or like delay, and the right into the left. And that's how we create a ping pong, going from left to right, left to right. So that's very, very cool. And as you can see, this already expands our possibilities by a lot. So, for example, we could modulate the feedback amount. We could also modulate the delay times. We could add more delays and also have feedback, like have multiple delays here. And once again, input this into the feedback as well, and so on and so forth. This will sound very cool as well. So there's really a lot of things you can do with this. And also, of course, this allows us to, for example, process this audio. So let me reverse this real quick again and put it back to the initial state here. So, for example, before it's being fed back into the delay, we could input a filter or a distortion way or something else, like really any kind of effect, and then put it back into the delay. And then, you can create very cool sounds by that. So really experiment with what you put here at the end, right? And use different kind of sounds from drum sequences to pads to piano and chords and melodies, whatnot. So you can really go nuts with this. Two more things I want to show you with this is, well, first of all, you could use, for example, cascading delays. It's similar to multitap delays, where we have, a 1 second delay and then a half a second delay also being all put into this tap out. But in this case, we would actually have first a 1 second delay and then a 1 second delay again of that delay, right? And then we can use feedback with that again, and then we can, cascade this again. And do this again. So now it will be a 3 second delay down here from this the starting point. And of course, once again, you import different things in between here. Filters, like, for example, you could use low res, which is a very simple resonant low pass filter, or you could use, for example, clip to make like some kind of distortion of any audio signal. And just input this in between and see what you can come up with. The last thing that I want to show is how we might use these delays with maybe, for example, another kind of input, and rather make this, for example, something rhythmical. So in this case, let me build a little synthesizer real quick with a sine wave, cycle object. So I have now created a little sequencer here. It's very, very basic, and also I think there are a lot of other and better ways to create this kind of sequencer. So this might be something for a future video, kind of like how to work with sequencers and how to create sequences of pitch and stuff for basses and drums and melodies, whatever. But this will do the job for now. And sounds like this. Of course, we can also increase the speed. Exactly. And now we want to use this with a delay, and we want to make this kind of rhythmic so that the speed, or kind of like the BPM, is corresponding with the delays, or the delays rather, the delay times are corresponding to the speed here. So let me maybe move this over here to make this a bit more neat. So now we can use this number box to adjust the metronome, so to speak. And we can also use this to adjust the delay time here. So now if I change this value here to, let's say, something like 300, we would now have a metro which bangs every 300 milliseconds, and at the same time we would have a kind of mono delay now, because both delays are the same, every 300 milliseconds, including feedback. So it will sound like this. So I forgot to put the output of the signal here into the tap-in here. So once I do this, you will hear the delay. And now with the original, it creates this very rhythmic kind of delay, of course. And we can also adjust this again and say, for example, I don't know, 300, let's do it on a bit faster, 230. Just the envelope a bit. Increase the feedback. And of course we could also say, for example, divide the second delay, or rather like the right channel, by 2. So now if I do this 230, I will do this, right? Or we could say divide it by 3 or something. And then we can make this ping-pong again. And that goes back and forth, the feedback. Very cool. I think that's very nice. And you can really experiment with this. And this is like one basic example of how to work with rhythmic delays. Of course, one more thing would then, of course, be to look into the corresponding multi-channel object of tap in, tap out, and delay, which allows us to more easily create multi-channel delays, and adjust their panning, their delay times, and, if we put effects on them, pitch shifting, whatever, that will be a lot easier. And it's something very interesting, which you might want to look into, or maybe I will do a lesson on this in the future. But for now, I think this is the most basic kind of way on how to use delays. And once you understand how to work with these objects and what their possibilities are, I think you can do a lot more then. So I hope this was helpful. If you have any questions, leave them down in the comments below. And I hope to see you in the next one. Goodbye.